time is up and it's time to start working. So here goes nothing. So I made this little chart to have more visual clarity of what is done and what is not in the CPU. So we can totally notice that we are a little past half of the instructions that we need to be able to support in our project, in our emulator. So the next, I will keep following this. I will continue this in order as much as possible, unless I make unless I change the order for the sake of having stuff implemented together. So the next on the list is the exclusive OR. Let's open that one. And yes, it makes an exclusive OR performed between A and an address memory. And we have a lot of addressing modes to support, including immediate, so we can make an exclusive OR to the next byte in the program. So the Twich how we are working for now, and let's make the instruction before the test, because I think that is more it will be easier to handle that way. So we are going to put this OR after decrease Y. So let's find decrease Y. Let's add our OR in here. Exclusive OR. We don't assign any opcode yet, and we are going to erase the method. We're going to call it exclusive OR with register, and we are going to pass a register, by default register A, and an addressing mode, immediate first, and let's make many copies of this. Actually, we'll erase immediate before creating the copies, and let's address the rest of the list. Let's do our usual tiling and work in distraction free mode. So we have immediate 0 page 0x absolute x absolute y indirect x, and one more indirect y. So all of them will take the register A, and now we can start filling the opcode. So we're starting from the top: 49, 45, 55, 40, 5D, 59, 41, 51. Okay, Number of bytes, 2 bytes, 2 bytes, 2 bytes, 3 bytes, 3 bytes, 3 bytes, 2 bytes, and 2 bytes. Number of cycles, first is 2 cycles, oops, 3 cycles, 4 cycles, 4 cycles, 4 cycles, 4 cycles, 6 cycles, 5 cycles. Okay, so now we have to write the function. So let's go over here and let's create our exclusive OR function. Func exclusive OR with register and P register 8-bit and P addressing mode. We get the address, we get the value. I will copy this. Oops, this is dead code. I will remove it in this commit. Did something wrong? Okay. So we are getting the address from the addressing mode. We are getting the value, and now we have to make the exclusive OR operation between the value of the register and the value that we have read from memory. So how is exclusive OR? In Python or GdScript? Python exclusive OR. So there is a Tor. Seems like it is the same symbol as mentioned in the documentation here. So let's try it. Value exclusive OR P register dot value, and we want to update 0 and negative with this result value. So P register is gonna be equals to the result, and we want to also update 0 negative with the result. So that should be all for our instruction. That alone. Now we have to create our test case. Let's make it full screen for a moment while we manage some files. Let's find our test folder and let's create a new script for the exclusive OR with the test template. Create, and let's first of all fix the ordering of these functions. I should probably fix it on the template so we don't have to rearrange it every single time. So 0 page, then 0 page X, absolute, absolute X, absolute Y, indirect X and indirect Y. So we have to invert absolute and 0 page. Okay, awesome. So Let's take the chance and update the template for this. So let's find our template file. I will open it in the other monitor to avoid as much noise as possible. Here it is. Opening with code. So we want to invert 0 page X and absolute, and we want to invert 0 page X and absolute from here as well. And we can make a couple more changes, like adding some boilerplate code to this test. So we are loading a number and nothing else. So this is the LDA test with immediate, and this is all we are copying. We don't care of anything else. We could add like a couple more flags, like the overflow and the carry flag, just to make sure we are we can simply delete in case of necessity. So we can also add a print, and let's copy it from here, and let's copy this from here. This will be just a little less effort in the future, getting mainly the initialization of the CPU. Maybe we should also copy a couple of examples of loading memory into the initializing memory into the mem. So let's take an example of 1 byte memory and an example of 2 bytes memories with an offset. So this is just boilerplate stuff. We are going to likely delete it over time, and we will just keep what we need for the test. So in this case, let's start with let's copy this from LDA for the last time, I hope, and let's start creating a test for the exclusive OR. So first of all, before we do that, let's change all of these to uppercase to lowercase. Edit, convert case, lowercase, and let's complete the function name. Exclusive or with register A, and we can start filling the information of the opcodes. Instruction free, and let's start with this. Is 49. Second is 45. Third is 55. Fourth is 40. Fifth is 5D. 5, 9. Last two. 41 and 51. Okay, and let's copy this, and let's just skip the first part and the print. Let's replace the function name in the print, and this is what we want to test. So we are going to load a binary and then make a test, an exclusive OR with another binary number. So if I remember correctly, an exclusive OR will only set a bit to 1 if only one of the two binary numbers is 1. If both of them are 1, it will set that bit to a 0. So let's do that. Let's put this one to a 0. So we are going to keep this one, and let's keep both of these to 1. So this one should be a 0, and let's put some random other stuff like a 1 in here and then 1 in this other side, and that should make these, no, yes, these just are 1s like this. Think so. Yes, so I think this should pass. This is not 0, but it is negative because this bit is a 1. So let's take a look if this works. Of course, we first have to add it after text day. Let's rename it to exclusive OR and assign our script. Save. Let's hit run, and it did not pass. Oh, I did something wrong. Could not convert argument find from nil to callable. What did I do wrong? And it is on line 31, but I am assuming it is referring to the last stuff we have added. Okay, so we forgot to write bin in this. So instead of assigning the callable, it was actually calling the function. So second shot. Okay, seems to have passed. Let's find our print. And we have an exclusive OR with register A with immediate has passed. So yes, now it is a matter of making the other addressing modes work. So this is 0 page. That means that we are going to access the first page memory. So let's find, oh, I closed it. Let's open it again, and here is my template, and we'll copy this memory right and put it in here, and I will use this opcode to access the first page memory address 03. This is the next. So instead of doing immediate management, we are going to access to a 0 page memory using this opcode with the memory number 3, and we will find this value, and it should perform exactly the same operation and find the same result. And we change this print and shoot it, and it seems to have passed. Here it is. 0 page exclusive OR. Next one, 0 page X. So that means it will get the memory, add X, and then find the value. So let's put a 6 in here, and let's load a 3 in the X register before. So it does 3 plus 3. So we can even write it like this, so it is more obvious. So first we are going to load a 3 and then transfer it to register X. It's OX, it was AA if I remember correctly. Tax, so tax is AA indeed, and then we can load the binary number that we want, and this one should be done and should pass. We have already tested our what did I do wrong? Oh, I forgot to change the opcode. We have already tested addressing modes, so we know they work. We are just making a uppercase, a newer test. So we are failing to make this. Why is that? We are loading 3, transfer it to X. Let's make sure that X is 3. I may have got it wrong. CPU register X, and it is indeed a 3. So okay. Oh, I made a mistake and converted the wrong byte. So I set the address instead of setting the opcode. So noob mistake. Okay, it passed now. Exclusive OR with 0 page X. Okay, next one is absolute. And for that, we are going to take the same as 0 page, but we are going to replace the memory address to something of 2 bytes. So let's take 4003. So before I forget, let's change the opcode, and now we have to load a 2 bytes memory address, because this is little endian. We have to set first the less significant bytes and then the high significant bytes. Oops. So this should be passing, famous last words, and it seems to have passed. Okay. So absolute X, it will be very similar to a combination of the last two. So let's take this absolute and let's add this addition of +3, and let's add these 3 first instructions that loads a 3 in the register X, and this without more changes except changing the instruction, of course, should already pass. And seems to have passed. Yep. Absolute. Yeah, I seem to have forgotten to change the print. Here we go. Absolute X exclusive OR. Okay, 3 more to go. So we are going to do the same, except we are going to test with the Y register now instead of the X register. So the test is exactly the same, except instead of loading the register X, we are transferring to the register Y, which is A8 if if I remember correctly. And we have to also change the opcode of our instruction. Take the print and give it a shot. Okay, seems to have passed. Absolute Y exclusive OR passed. Now comes the difficult ones. Let's take indirect X and Y. So let's copy this last example. And I always need to remember how is this. Did it take only 1 or 2 bytes for the indirect? It takes 2 bytes, so that means we can only point to the 0 page memory address. So we are going to point to 03 plus 3, and we are going to get a value from here. We are going to get 0x05 in example. And in 04 plus 3 we are going to take the second part of the memory address. Let's make it 0x40. So what does this mean? Let's add a write memory here with 0x4005. So what is happening here is that it is going to, let's change the opcode. Yes, this is the opcode correctly. So we are going to take a memory address. I don't need this anymore. We're going to take a memory address, add X. This is X, so let's put double A here. Add X and get the first value, and we are getting the little endianness part of the memory address. And then the next one will be the most significant bytes of the little endian memory address. So if I am not totally crazy, this should be working. A little to map again, we load a 3, transfer it to X, we load the binary number that we have been loading, and we are using 41 as exclusive OR instruction with the number 3. Because this is indirect X, we are going to take 3 and add the value of register X, which is another 3, and we get the memory stick, and we get the low byte, and in the next memory cell we get the big part, and then we have the value that we want to perform the exclusive OR operation. So let's give it a run, and it seems to have passed. Confirming. Okay, exclusive OR indirect X. So it has worked. So let's copy this, and the difference between indirect X and indirect Y is not only that we use the Y register instead of the X register, so we transfer to Y instead of to X, but also that the addition of the offset is not done to the first part but to the second part. So we are going to access directly into memory 3. Let's change the opcode. We access to memory 3 for the less significant byte, and the memory 4, which is the next one, for the most significant bytes. And to that we are going to add the value of y to get our binary number to make the exclusive OR. So we changed the print and gave it a shot, and we got exclusive OR working, I think, in record time. So this has been awesome. So let's commit this. This is secret information. Let's open our command line and let's see our changes. Git status. What is new? We registered our exclusive OR command, deleted this code, created a function for exclusive OR, added the test to our scene, and we changed our template script. So we reordered it and added some boilerplate code to the first iteration of it. So this seems correct, and this seems correct. So we have to also add. I accidentally closed that. We also need to add our test script. Git add, and we pass our test script and git commit. Implement exclusive OR instruction and create unit test. Let's see this. So we did have an issue. Let's edit it. Implementation and unit test for exclusive OR. Okay, let's make it an issue. And put it in progress. Did it create it? No, it didn't. Okay. So now git commit amend. Oops. And we can now say this closest 28. Git push origin main. And we are gone for good in here. Let's move this to a full screen window. So next, according to our sheet, so let's move the sheet to this other window, and we have completed the exclusive OR. So next instruction is jump. Let's close this one and bring this one, and next instruction is jump. Before I forget, let's edit this. Implementation and unit test for jump. This in progress. Copy. And let's edit some stuff here. Quick. This is the part that you never see, but I like doing everything live so people get used to the workflow. Alright. The next one is jump. Let's check what it does then. Sets the program counter to the address specified by the operand. No flag is accepted. It takes an absolute or an indirect addressing mode. So that means we are going to affect the program counter by setting exactly what is the 2 bytes address memory, or by taking an offset of how much to move it. Okay. So let's first make the jump instruction. And our jump instruction comes after increase Y. So after increase Y, we're going to make jump. Duplicate. We are going to take this is jump. It has no condition at all, and it takes non-argument except of the addressing mode. This is jump, and let's change the opcode. Oops, I am a little clumsy today. Sorry. So here we are, and absolute takes 4C. Duplicate this line. Indirect takes 6C. Both take 3 bytes. So indirect can take 2 bytes of information instead of 1. That is interesting. That means you can make big jumps. An original 6502 does not correctly fetch the target address if the indirect vector falls on a page boundary. In example, XXFF, where XX is any value from 00 to FF, in this case fetches less significant byte from XX as expected, but takes the more significant byte from XX00. This is fixed in some later chips like this one. So for compatibility, always ensure the indirect vector is not at the end of the page. Is this something we need to take care of in emulation? So this one is indirect, but not indirect X. we do not have an indirect without the X. So let's add it. Indirect. Okay, it matches. Okay. So now we have indirect without X. So I think number of bytes matches and number of cycles matches. Not the only thing missing now is creating the jump instruction. So let's create jump function jump, and all it takes is the addressing mode. We get the address and get the value. To the address specified by the operand. So this is more or less like immediate. We should read both as immediate. I suppose. I am a little confused. Should I use the get operand address? Or should we read the memory address manually? I think I will, to make sure I don't mess up, I will read what does the implementation of the instructor does. Let's try this and let's see the sample code in GitHub. And let's see how it handles what was the code? 4C and 6C. So indeed it reads the address directly from the program counter. So we are going to get memory read 16, and we wait, this is if p addressing mode equals absolute, and we are reading directly from program counter. And we set the program counter to this new address. And that is in the case of absolute. I could use match instead. Where is my music? It happens all the time. And indirect right. I forgot to say, maybe it was that. Yep. Oh. So in the case of indirect, we get the memory address exactly the same way. Okay, so it is indeed making the workaround for the bug in the 6502. Indirect reference. So basically it's read from memory 16 twice. So address is read the address, and address is read from this other address, but we have to also add the comments. Let's copy these comments and let's see if it is good enough for us to understand, and if not, let's fix it. I don't like spaces. Okay, replace the spaces. Come on. Okay, now we can comment and shift the comment. So let's see what it says. 6502 book mode with page boundary. If address 3000 contains 40, 30FF contains 80, and 31 contains 50. The result of shown 30FF will be a transfer of control to 4080 rather than 5080. I quite don't get it. In explanation, the 5502 took the low byte address from 30FF and the high byte from 3000. Okay, so I think I get it. So if address and OX00FF, that is the less significant bytes, take the less significant byte, is equals to OXFFF, then we have to apply the fix. Memory that I will just copy this because I am very confused and want to move on. So let's see, we are getting low memory from memory address, which in our case is address, and we will get the high memory from the first 2 bytes of the low level bytes of address. Is that right? No, from the high level bytes. And now we have to combine them. So first we are going to read this memory, and we are going to override in the case of the book happens. So it will be high shifted 8 bytes or low memory. And these are integer. Address is an integer, and I think I am ready to set program counter to value equals address. Okay, so we did, we cheated, but this is the way to go. When you don't know what to do, find an example. So question is, how do we test this? I have no idea. So I decide to not test it. So I don't feel right not testing it, so let's test it. New script, jump goes after increase y, right? Yes, after increase y. Adding a node, renaming it to jump, assign the script, boilerplate in place. So let's try to make some sense of this. This is starting at 8000 if I am not wrong. Let's try to split it a little. So first of all, let's make a jump. Oh, I am modifying the wrong script. What is jump? This is jump. Okay. I was being dumb, and I have corrected myself. Change to lowercase, and we only need an absolute. And indirect, not even X. is jump. And code is where is my opcode? 4C and 6C. 4C. And this is a 6. And this is a 6. And we copy the function name to here, and we are not affected by flag. And we are going to check. We don't need to any memory addresses, and we're going to work with some instructions. So the first instruction is going to be jump to an absolute location, and the location is gonna be some value so this is equivalent to jump to the memory address 80OA, and this start in 8000. 1, 2, 3, 4, 5, 6, 7, 8, 9, and this one should be the 10th, which is the A. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is 10. Okay, seems correct. So what we are going to do is load a 7 in here. So this is the trick. If this jumps, it will load a 5. If it doesn't jump, it will load a 7, and then it will terminate the execution because it finds a break in here. At the end, when this finds, because it jumps, the register A should be equal to 5 because it should have jumped. So let's test that theory. Give it a shot. And seems to have passed, which I am very impressed. Is it true? Can we find our pinning? It is for it. Jump. Yes, jump absolute have passed. So that is awesome. And indirect, let's copy all of this, make a paste, and indirect, instead of taking the direct values, we are going to store these two values into a memory address first. So cpu.address sorry, not address, memory, write memory, memwrite, memwrite 16. It takes little endianness. Yes, it takes little endianness. Okay. So I can store into memory OX4003. I can store the actual memory that I want to check, which is OX8008, and the function will make sure to split this and store using little endianness instead of high endianness. So that will work, famous last word. So now we need to change the instruction that we are executing, and instead of passing the direct memory, we are going to pass this other memory, that is 0340. Right, so this was a literal and this was a memory. 4003. Pa-pa-pam. The rest should be right. Let's change the print and let's see if it works. It seems to have passed our test. So jump indirect word. We should add a test for the book case. So let's see our command to try to understand what is the book about. So this is the memory that we want to test, 30FF. And let's do that with the indirect. Copy this entire instruction, and we want to take this memory instead of this memory. So this would be OXFF. Oops, it's a 0, not an O. OX30, and it will take the low value from 30 and the low value is sorry, I am confused. It's OA. Okay, and the high value from FF or from 00? No, wait. Okay, so it's from 30 00 will take the low value, and from 30 FF the high value. Is it like that? And let's check our example. The low byte from 30FF and the high byte from 3000. So yes, this is, wait, the low from 30AA, sorry, 30FF. So this is inverted. This is what you are trying to tell me. Okay. Missing a comma. And this should be 30FF, and it takes from 3000 instead of 3100. Okay, that seems correct to me. Uh, 5602. What's that the name? 6502. It was inverted. Yeah. So let's make sure this passes, and it did not pass. So we should find out why. What is the value of A? And it is 0. So we did something wrong. The number of bytes seems to be correct in both scenarios. So FF 30, so it goes to 30FF and gets the low byte, then goes to 30 and gets the high byte. So seems like we are doing something wrong in this case. So let's see if we are doing it wrong. And execute. So it did not enter the condition. So we did something wrong indeed. So we get our address from the program counter. We get 30FF. Wait, no, it's okay. So we have two indirect cases. Let's rerun both. And the first one should work without entering this corner case. I have a boo-boo here. It was meant to be 00FF. Okay, so let's give it a shot now. And this is why we have unit tests. I am glad I made it, because otherwise I would not find it until very late. Okay, so jump is finished. It's instruction 29. Let's add our test and let's check for other changes. We added indirect. We added the two new opcodes. We added the jump instruction. We did not handle an invalid addressing mode, so I should add an assertion in case of an invalid addressing mode. So let's see, jump, and in any other case assert for invalid addressing mode for jump instruction, and the addressing mode is the addressing mode. Okay. Let's add this new line. Git commit implement a jump and add unit test for it. Closes 29. Awesome. So we are another one down. Next one is JSR. Let's find out what is it about. Goodbye. JSR, jump to subroutine. The JSR instruction pushes the address -1 of the return point to the stack and then sets the program counter to the target memory address. Processor status after changes nothing and only uses absolute addressing mode. Okay, so we have jumped to subroutine. So the thing is, we have not done anything with the stack yet, and we will have to investigate that. Do we need to pass an addressing mode, or we can just assume it? Let's just pass it and make an assertion. Absolute. Okay, perfect. Invalid addressing mode for jump to subroutine instruction. Okay, awesome. So this is absolute, so we will not have this issue. So we should simply get our address and set the program counter, but before that, oops, what is that? Before that, we have to push stack. And we want to push the program counter -1 according to the to what this says. Pushes the address -1 of the return point on to the stack and then sets the program counter to the target memory address. So I think it means it passed these 3 bytes. So before this change, we are on the first of these 3 bytes, so we have not added the other two. So instead of -1, it should be +1, or better said, +2 -1. Okay, so we don't yet know what push stack does. All we know is that it should be an 8-bit integer. No, wait. It is not an 8-bit. It should be a 16-bit because it is the value of a program counter. We don't yet know what it does. So to clarify this, let's see what the shunt subroutine does in the example from our tutorial. Oops, that is not right. And the instruction is 0x20. Shunt to subroutine, so it gets, it makes exactly the same math as I did. So it has a stack push unsigned integer 16. So there are functions for 16 and for 8. Let's rename this to stack push instead of push stack. And let's name this 8 and 16, and this will be 8-bit address and 16-bit address. Target address will be reading the program counter and then sets the program counter exactly what we did in our jump to subroutine, right? So this will be stack push 16, the same as this guy did. And let's find out how stack push 16 works. So it takes the hover and lower, and it has stack push, and calls the 8-bit version of it. Okay. So variable high integer equals p16 address. So the high value are the most significant bytes. So we want to shift this by 8 to the right, and the first 8 bytes are discarded. The low bytes equals to 16 and OXFF, so it will take only the first byte and forget about the rest. So now we can stack push 8. Was it first the low, I guess, and then the high? Assuming this is little endianness. Oh, it's actually first the high and then the low. That's interesting. Okay. But the stack is written in reverse, so it makes sense. So we have the stack push, I am assuming that we also want the stack pop. Oops, punk. And stack pop 16. So for the 16 we are getting high and low in the invert order, so first low and then high, while in stack pop 8. And then we are going to create the 8-bit version of it, so it will return the high memory shifted 8 bits and the low memory without any change. So this is ready, and these are the important ones, the ones that we want to find out how they works, because we don't yet have a stack in this NES. Yes, it's stack pop. So we have a stack pointer, which I assume is just an unsigned 16-bit integer. So the question is, what does it initializes to? Oh, it's unsigned 8. Okay. Stack reset. So in reset it is initialized to stack reset. Okay. So let's see. We seems to not need a register. So let's go bar stack pointer. It's an integer. We are going to create a constant for the stack reset. Like in here. Oops. And this is gonna be, wow, FD. And the stack itself so this is an integer, this is an integer. So how does this work? It goes from FD up to 100 or inverted? Stack pointer. So in reset we should reset it to stack pointer. Do we have init to take care of? I guess we are going to set it like this. to stack reset like that. That's all for now. And what is stack for? So when we pop, we're adding one. So that means that it decreases when you push. So I see. So stack pointer is an offset, and stack is the start of the stack. Okay. Let's set my music again. So let's make a function get stack address, and this is going to return stack plus stack address, sorry, stack pointer. Then we have advanced stack should be advanced. Let's say on stack push, so it will be a little more obvious. It does not return anything, and it will be stack pointer minus equal 1. When we push, we subtract 1, and if it is less than 0, stack pointer we add 0x0000. So basically we are wrapping around. So we make the counter function on stack pop, and it will increase 1 to the stack pointer, and if it is bigger than 0xff, we're going to subtract 0x100, and that will make the wrapping of the unsigned 8 integer. So stack push, I think we first set the value. Let's write it and then we confirm. Memory memwrite, and we pass the get stack address, and we store the value, and then we advance the stack on stack push. This is a push. So we stored the value and advanced it. In the case of pop, I think we have to first come back and then read the memory. memory main read get stack address, and we return the value. Is this correct? So let's compare. Stack push. Stack push, it writes a stack plus a stack pointer, and it writes the data, which is an unsigned 8, and then advances stack pointer wrapping around. No, subtracts. Okay, so on push it will subtract, so that is correct. And on pop, it will first add one wrapping and then read the value and return it. So it seems to be working as expected, or it seems to be doing what is expected to do, but the thing is I have no idea of how to test it. But we can at least make a jump and see if the right memory address is stored in the stack. So let's create a new test script. Oh right, we also need to register this, right? So GdScript goes right after jump. GdScript. Let's duplicate one of these, and the function is jump to subroutine, and addressing mode is always absolute. It takes 3 bytes and 6 cycles, and the opcode is 20. So I think, oh, and shop to subroutine. So yes, okay. So we are going to create a test for this, and we are going to duplicate the jump script, the jump test. Oops, forgot to rename it. So there are a couple of things to do. One is we don't have indirect, we only have absolute. So we got rid of half of the word, and we want to rename the instruction GdScript, and the function name is jump to subroutine, and the I did it wrong, and the opcode is 20. Okay, 20 jump to subroutine, absolute jump to subroutine, and this seems correct. And we are going to make this little assembly function, and this will have exactly the same, except that we are also checking the contents of the stack memory. So what we should probably do is reading, getting the stack. So because the execution has run, I don't feel bad about popping the stack. So let's say stack pop 16 should be equal to the location that we was before jumping, which was this. So this was 8001 and 8002. OX82. I think this is the test that we want to do. Oops. This should be uppercase passed. It's like I messed it up when converting to lowercase. Let's test, and of course it didn't run because I never added. So let's create JSR and let's check now that it runs. And it failed. And why did it fail? This function, so we don't have the result of the stack pop, so we are going to set a breakpoint here and get into it, and we can see what is low and high memory, and they are both 0. So we are doing something pretty wrong. Did we make the right call? Come to subroutine. Okay, it is not executing it because I am making the wrong jump instruction. Okay. So now we are getting values for high and low. Indeed. Advance. And now we have a breakpoint and advance, and the breakpoint did not fail. So we have passed our jump subroutine. So that is another one down. Awesome. And status, copy, git commit, git add a new test, git commit import. So we added our constants, initialized the pointer, registered the jump to subroutine, reset the pointer on reset callback, and added the jump subroutine, added the stack push and pop functions, and changed the casing errors in the prints, added the new test to the scene. Oh, and now I have to enter my commit message log. Implemented JSR instruction and added unit test. Closes. This one should be 30. Let's confirm that out really fast. Oh, this one got closed and maybe I forgot to push it. We check it right after doing this. Let's convert this one to a new state. And yes, it should close 30. Git push origin main. Okay, now this one should go away. Yes, I had forgotten to push before, that's why they both disappeared together. Next instruction is load X and load Y, which is very similar to load A. So we have been 2 hours on stream. Do we continue right now today? We can give it a shot. I would love to have some more progress. Yes, why not? One more. So let's take the... Oh, I already created the issue. And the NES CPU. So we already have load register. So we should be able to create LDX and LDY. Just reusing this same code. So, and load X and Y takes less. Wait, I am doing something wrong. This is LDX. It takes less variants of addressing mode, so we don't have to do all of them. Let's take a peek of this. Bam bam badam. Let's put it in our side. Put this in this side and enable distraction free mode. So load X, X0 and negative equals to M. It is exactly the same as load Y, except that the variants of 0 page X and absolute X are going away. So what do we have? We have immediate, we have 0 page, we have 0 page Y. We have absolute, we don't have 0 page X. We have absolute Y and we don't have any indirect. So once again, immediate, 0 page, 0 Y, absolute, absolute Y. Okay, let's fix the opcodes. Immediate is A2, 0 page is A6, 0 page Y is B6, 0 page, absolute is AE, and absolute Y is BE, and that is load X. Okay, and now we are going to make a copy of this and create load Y. Oops, I should have put it below this. Never mind. So let's make some changes in here. This is load Y. This will change the Y register, and the addressing modes are immediate, 0 page X instead of Y, absolute X instead of Y. And opcodes are A0, A4, B4, AC, and BC. Quick check on the bytes and cycles. LDX first. 2 bytes, 2 bytes, 2 bytes, 3 bytes, 3 bytes, correct. Cycles, 2 cycles, 3 cycles, 4 cycles, 4 cycles, and 4 cycles. LDY, 2 bytes, 2 bytes, 2 bytes, 3 bytes, 3 bytes, 2 cycles, 3 cycles, 4 cycles, 4 cycles, 4 cycles. Okay. So this should be all for implementation of load the register X and Y. So now we need to test them. So let's do I create a new file or duplicate LDA? I will create a new one. Create a new test, and this one will be load X. Oh wow, I messed it up there. Let's delete the script and create it again because it put new script as class name. Load X. So let's take this stuff and change it to lowercase. This to lowercase, not that it matters, and all of these to lowercase. Okay. So let's get rid of what doesn't need to be in here. Instruction free. And this is load X. So it is immediate, 0 page. This goes away. Wait. 0 page Y. Absolute. Are you looking right? Yes, an absolute Y. So now I need to rename this to this. Okay. And we don't have absolute X, and we don't have any indirect. And yes, we don't have any indirect. And this should be correct. Function name. Over here, over here, over here, over here. Function name is load register X. And let's start filling the opcode. immediate A2 zero page is, where are you, A6 zero page Y, B6 absolute, AE and absolute Y, BE. Okay, so for loading we don't need to write on memory, we just need to run load of the value. Actually, let's copy LDA entirely because it makes all the cases for the flag. And let's change load A for load X and register A for register X. This one should pass as is. We can give it a shot. Did I add it? LDA, no, I did not. Duplicate LDX, and let's assign the LDX script, run it, and it passes. Perfect. And from now on I should be able to copy the test from LDA and just change the instructions. So instead of A5, A6, and this is the function name and should pass. Wait a second, yes, so this is register X now. Okay, awesome. Zero page Y. I think we don't have zero page Y in LDA, do we? No, we don't. So it is gonna be easy in theory. So we can take zero page X and we are going to replace transfer X, transfer Y, and we are going to replace load A for load X, and of course change the register in the test from A to X. And I think this is all. Does this pass? It does. We're still pacing. Zero page LDX immediate, zero page Y. Now comes absolute. Here is absolute. This is why I did not just copy the entire script. So we are going to test against register X, and we have to change load A for load X. Which one is load A? This is load A, testing, and seems to have passed. LDX absolute, and the last one should be absolute Y. So we are going to change load A for load X, and we are going to change register A to register X and give it a shot. Okay, seems to work. So we have load X fully tested and running. Isn't that great? So now, yes, I am going to create a duplicate of this script because it no longer has the repeated stuff. So I can replace LDX for LDY. 2, 3, 4, 5, 6, 7, 8, 9, 10. I can change underscore X for underscore Y. So let's from the start. Yes. We want to change the register in the test. The print looks correct. Okay, perfect. So now the part that is missing is replacing the instructions. So we have to get rid of this opcode because those are the load X ones, and we want to fill the new ones. So here we go. Load Y. Distraction free, and immediate is A0. Zero page is A4. Zero page Y is zero page X is B4. This is zero page X, not Y. And this is absolute X, not Y. Zero page X, absolute X. Okay, awesome. Forward. So absolute is AC. And absolute X is DC. Okay, awesome. Now let's check one at a time. So for load immediate, we have to change the instruction. And that should be all. Famous last words. For zero page, I think only the instruction as well. 0 page X, we have to change the instruction, but also we want to change the transference. Instead of transfer to Y, we want to transfer to X. And the print. Absolute. We want to change the instruction and nothing else. Change the print. And absolute X. We want to change the instruction and the transference. So we change the instruction and the transference. Instead of transfer to Y, we transfer to X. And if I am not crazy, this should pass, but first I have to create the node to add the test. And assign load Y script and run. And seems to have passed, so we have LDX, immediate 0 page E, absolute and absolute E, but we have an error in the name of this string. So absolute Y is this print. Okay, now it's LDX. Now LDI immediate 0 page X, absolute X. All passed. So awesome. With that, we have all the load functions working for the 3 registers. Git status, git add this, git add this one, git add import. We registered the new instructions. We did not need a new function to make it work. We just reused the load A. We added new tests to the test script. Git commit. Implemented LDX and LDY instructions. Added unit test for them. Closes 31 if I am not crazy. Yes, 31. Git push origin main. Okay, 2 less more. Okay, so it's been 2 hours 15 minutes or something like that since the start of the stream. I think this is a good time to stop for today. So let's take a look to the current state of the project. From the first half is totally done. From the second row we are missing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And from the last one we have done 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can say that we have almost 75% of the instructions implemented. So that's a quite lot of advanced. We have 75% of the CPU working. Thank you very much for watching and see you next time.